Yeah, sorry. Um, Hi, so I'm Charles Pagia, and I'm the Java programming team lead. Um, and um, to introduce the project, so the project is called the Cognitive Telescope Network Internet of Telescopes, and basically, we're trying to put it simply, we're trying to get um, the IBM Watson supercomputer interfaced with an array of telescopes. So how we're doing that is we're implementing the steps to get a telescope functioning and responsive to just a single computer. So we're going through the process of creating the commands to um, allow the telescope to be moved by a computer so that we can then integrate that with IBM Watson and it can take charge and control the telescopes. So we're trying to make our code manageable and easy to apply to a whole bunch of other different types of telescopes because we are working with the Takahashi Tema telescope ourselves. So just going back really quick, there are we have 5 groups that are going to be presenting here today. We have the Java programming group, the protections group, the server group, the Swift programming group, and then the imaging team. And they're going to be explaining more of what they do to make this whole project happen when they get to talk on their part. And then this is kind of just a general overview of the project. So if you were to look at the chart here, the telescope's going to be in an observatory and it's going to be connected to a server, the Indigo server, which is an astronomy server platform that allows you to control a telescope through the server. And that's going to be hosted on how we're doing it currently is we have the server hosted on a MacBook, which then we connect to. The Swift team is coding the application in Swift to control the telescope by interfacing with the Indigo server. And the Java team is essentially doing the same thing, but in Java. We have an imaging team that then takes the images from the telescope and processes them. And then we have our server team, which is working on getting the Indigo server all maintained and making sure everything connects properly. And also in the future, they'll be working on getting the telescope and the server connected better to IBM Watson, the supercomputer. And there's also the protections team, which is working more physically on just engineering the telescope that we're testing this out with, the Takahashi Tema telescope, so that it does not break and etc. So going more specifically to the Java team, the Java programming team, I'm the team leader, and then there are 3 other members of the team. We have Angelica Madera, Amir Stevens, and Samia Ahmed. So what we do is, like I mentioned earlier, we're coding the functions to allow the telescope to be controlled via via a application that's coded in Java. So our goals for the semester is that we wanted to implement a kind of multi-threading framework to the system, to our Java application, so that we could implement a simultaneous execution and listening of instructions, which is required so that the telescope is able to output information, and just such as where it is located, the time, and just like calibration details. And then it also needs to be able to execute and read instructions that you send it in, so that when you send it a command, it will listen to that command and do what you want. So that's obviously important so that IBM Watson is able to eventually interface with the telescope and get it functioning and move it and such. And another goal that we had for the semester is we wanted to be able to catalog some missing information, which in terms of the Indigo documentation, Indigo, like I mentioned, is the server software that we're using that the telescope connects to. However, the documentation on it is very poor online. Specifically, the information on creating server sockets or just clients to control the telescope is very sparse. It's not easy to read. And due to that, we're trying to have to learn how to use the Indigo documentation to better suit our project well. So in previous semesters, last semester specifically, they had restarted from the previous code in Python in Java after they encountered errors with getting their Python code to interface with IBM Watson. So last semester they started coding in Java. So they started with a clean slate. We're kind of going off that. They also were able to establish a connection to the Indigo server using a Java socket. So basically there's a connection between the using the Indigo server. The telescope is connected to the server, which is hosted on a MacBook in our case. And the socket is essentially a computer is hooked up into the same port and able to read on that line, so it can send messages to the telescope and also read messages that the telescope is communicating. And then we also, last semester, they also started documenting some functions of the driver. For example, if you want the telescope to move in a certain direction, you have to send a certain line of commands to the telescope. And last semester, they started documenting that process because, as I mentioned earlier, it's not well documented on the Indigo documentation. So building off of that this semester, we were able to, well, firstly, we had a lot of issues with documentations on connecting to the server. Angelica will touch on that in a later slide. And we had to kind of rewrite the documentation on how to connect. And after we were done with that and we were able to connect, there was some errors that we had to fix. Specifically, there was some version errors with the JDK that we were using, and there was also some confusing, just errors with the directories. So it's more like organizational dependency errors that we had to fix the first part of the semester. After that, we started working on organizing the documentation of the server requests and responses to XML files. Amir will be able to touch on that in a later slide. And then we also worked with various ideas of how to implement this multi-threaded server response and execution parsing. We first thought of using JDOM, which is a XML parsing like library, or but we ended up using XPath, and we created an XML parser because the telescope communicates through the Indigo server using an XML format. So we had to be able to parse that so that we could really like read the messages it's sending and be able to send them back. So Amir will now talk about that XML parser that we created this semester.
Okay, so XML parser we created this semester is on the screen before you. And what it does at the start is it goes ahead and looks for commands, which the syntax for the start of the commands, less than with the /. After it goes ahead and finds a command, it'll go ahead and take that command and it'll strip it apart of the different attributes that was sent from the server. It'll go ahead and take the device name, and it will take the various function commands and arguments located within the string device and the string name variables within the function. The long if-else statement structure that is there looks for multiple things. The first is looking for if the device is if the command that's sent comes from the actual physical mount driver that controls the movement of the telescope. This is both a physical thing and part of the software, which allows us to send various commands to the server, not only changing the location where it's sent or the time response delays and things like that. The XML parser, ultimately, its goal is to output the responses of the server into a readable format for us. So when we go ahead and do the documentation, we can look at a static sheet instead of the continuous scroll that the server will send as it continuously gives us information. Overall, the parser allows us to create different functions as well. But from the inputted information, we are constructing our own functions to then go ahead and send back to the server as well. Now, Angelica, go ahead and talk about documentation.
Yeah, so for the documentation, we had a little bit of troubles as a team. So due to the Google storage quota that was implemented this semester, all of our documentation from previous semesters were wiped out. And that was definitely an issue because only 1/4 of our team members had previously worked in this IPRO. So we basically had to reinvent the wheel and start the team from scratch on our step-to-step documentation. And this involved outlining how to gain access to the IBM repos, building the Docker container in our individual local machines. And we all had like very different local machines, and it took a while because some of them were faster than others in building that. And we also had to figure out how to configure the Indigo server to ensure that there was proper functioning of the telescope, and providing additional documentation to clarify both the contents of the CTNT.com repo as well as the Indigo documentation that Charlie mentioned. So now we talk about our next steps. As Charlie mentioned, there's still a lot of work that has to go on in the Indigo server documentation, as well as figuring out ways how we can optimize those functions that we are receiving the communication to and from the client to the Telescope server. And also making sure that we get multi-threading working better. So multi-threading meaning that we receive messages from the server, and we process it and we output it so it can be sent to the telescope, and it can do its proper functionality in a reliable way. And our way of doing it was through a REPL process in which we read the data almost like a while loop, where it's constantly sending data that we're trying to acquire, and then we process it with the XML parser that Amir was speaking on behalf, and then we spew out all of the data so we can provide functionality to the telescope. And we also want to make sure that we keep into mind the errors by making sure that we implement try-catch blocks as well. And that's all from our Java team. And I'm going to pass it over to the protection team.
It's working.
Okay, okay. Can you hear me?
Yeah.
Okay. Okay, my name is Leticia Reyna. The protection team's objectives are to monitor the telescope to prevent collisions with the mount or the ground, and to establish a successful connection to the server, enabling communication between the telescope and the server. And finally, to manually shut down the telescope if the autonomous code that controls its movement and collision prevention fails to operate correctly.
Hello, my name is Arturo Ariola, and when it came to the telescope setup, we would mount it by positioning the telescope lens towards the east direction. We applied cool noodles to the telescope to provide an additional layer of protection, securely fastening the telescope to the mount, configuring and launch the server on the laptop to enable communication with other teams, connect to the power supply, to the mount to ensure the smooth rotation, while also connecting the power supply to the telescope to power its motors and control the system. Connect the laptop host to the server to the telescope, and connect the laptop with the server to the mount with the motors. Then moving over to the safety concerns. When operating the telescope, it's always important to be aware of the potential hazards, and that being since there was no knowing where any of this like dead zones were because of what all the documentation that was lost. We had to ensure that everything was being watched and monitored properly in case something was set improperly, and so that had to be automatically shut down. The weather conditions as well. Avoid using the telescope during extreme weather conditions such as high winds or heavy rain, and take appropriate precautions to protect the equipment. And continuing with the safety concerns, overloading, checking the manufacturer specification for weight limits before adding in any unnecessary equipment, and avoid overstressing the telescope. When it comes to cable snagging, being careful not to damage any of the connections to the cables or the devices by pulling or snagging the cables. And mechanical failure. Watching for unusual sounds or movements during the telescope operation, and promptly address any issues to prevent further damage. And previous states of work.
Hi, my name is Glenn, and I'll be presenting the previous state of work. Previous state of work were based on previous semester were adding a Raspberry Pi to the system and connecting to Arduino to send a message to a server. The ultimate goal was to have the Arduino trigger the Raspberry Pi to talk to the server and send a stop command to the telescope instead of just powering down the whole system. With the method, there's all solutions such as setting a relay shutdown to the system for some amount of time, such 10 seconds, and then reboot the system and then tell the server to position back the telescope to a normal safe position. Progress for this method had been started with the previous protection team, but then the Raspberry Pi data were deleted by OTS, so we couldn't continue with this method. Another method of state of work was to make a new housing unit for a power supply. Well, this method is to just not replacing your transportation box, but to protect the sensitive and components of the wires that's being connected to the telescope. With the method, there would be use of with the CAD modeling and 3D modeling software to do it. Essentially this model were to make it big enough to fit on the stand, so all the wires were to go inside the this housing unit and then lead to the telescope, so there weren't any wiring being tangled or disconnected when the telescope was being rotated.
So with the current state of work, we're using the pull noodles around the telescope to provide a cushion of protection and can easily be customized to fit around different parts of the telescope as needed. The soft mold material can absorb the shock of accidental bumps or drops. Pool Noodles creates a soft barrier between the telescope and any hard surfaces. This method can extend the lifespan of the telescope and prevent scratches and dents. It is practical and inexpensive solution for amateur astronomers or anyone who transports the telescope frequently. Additionally, pool noodles are flexible material that can be easily removed or repositioned if needed, making them a versatile choice for the telescope inspection.
All right, so our future plans, we came up with 3 plans. And the first one is adding a switch bot as a kill switch in case the telescope becomes unresponsive and it can spin uncontrollably, and it's just there as a safety protocol. And then the second picture that we have is installing a box around a telescope, and it's gonna act as like a cushioning system so that when something bumps into this the telescope, we have this box to be able to prevent the telescope from getting damaged. And then the third one is using an airbag, like product to protect the telescope in the event of collision with any object. So basically, we came up with these 3 plans as like to protect the telescope.
My name is Christian Leva, and I am the lead for the server team or the systems communication team. We also had Jacob Holtz, Carla Pardo, Tim Stack, Matt Ventrelli on our team. So for our background and purpose, Indigo is the protocol that we were using for the semester. This is built on the Indy protocol. And as previously mentioned, Indigo has pretty poor documentation, but it's built for astronomy use. So that's what we used. And the purpose of our team is to work alongside other teams and ensure that their workflow is as smooth as possible. And if there's any issues, then it would be our responsibility to fix. So here we have the Indigo Sky. Last semester, this was hosted on a Raspberry Pi and using Python. This semester, we decided to use Docker so that it could be containerized and it could run on your local machine. This would make changes easier to make because you could just save any changes to code on your local machine and it would be saved in Docker as well, as opposed to making changes on a Raspberry Pi where you would probably need to download code and upload it to the Raspberry Pi every time. And you can have multiple Docker instances and you can spin up any Docker instance that you would need instead of having, again, the hard copy on the Raspberry Pi. Some goals for our team would be to communicate the IBM's choice of server. We were in discussion with Ron, and they are transitioning to using IBM's cloud. So we would need to be able to be flexible with that. And using the Indigo protocol to communicate with the remote telescope and send commands. And lastly, create a UI with IBM's Carbon for easy access to the Indigo server. And here we have a picture of the flow of the UI that we would create. So last semester, the server team tested the auto restart rule for Indigo. Unfortunately, all that work was lost, so we had none of that work to go off of. Currently, for our team, we were using a Mac laptop to run it. And there was contingency plan for when the server stops, crashes, closes, fails, etc. LaunchD, which is a unified open source service management framework for starting, stopping, managing daemons, application processes, and scripts on Macs. It cannot interact with directly, so instead we use launch control to issue commands. During system startup, LaunchD is the first process the kernel runs to set up the computer. What we did this semester, we communicated with the Indigo server, and we also had to do research on the MQTT protocol. Originally, we were using Python, but then we had to switch over to Java. We were also parsing data from the telescope to finish some unfinished API functions. And towards the end of the semester, we started making progress using Carbon to create a UI for easy access to telescope information. And we made some plans for future semesters to advance the Carbon code.
Hi, my name's Initia Shandrive. I'm the team lead for the Swift control team. And our team is Abdul Mohammed, Sarah Mueller, and Favara Bondarenko. So what we do, our objective is to create a Swift software application that connects via Cocoa MQTT to the telescope, to send signals for telescope movement or tracking different signals, different astronomical bodies. So for the tracking feature, we also manage an interstellar database from which a user can both reference and also observe in real time. But the user is also able to preferentially set the telescope's motor rate and speed. And so we worked directly with the Swift imaging team using iOS native environments, and as well as the protection team to make sure that if anything goes haywire, that with the code they would be able to manually stop the telescope from going in a different location. So telescope movement at this point, it's pretty much the same as it was last semester with the refined right ascension and declination movements, the adjusted motor speeds when nearing the target. And so they began integrating the movement code that executed these movements. And so our job was to pick up from where they left off with this. So IBM Communications is what basically makes this possible. We use the lightweight MQTT protocol that provides the accessible interactive avenue to not only use this on a Mac, but hopefully to transition to any iOS device in the future. And it gives us the necessary, it gives us the necessary, oh, sorry about that. I went way ahead of myself. So yeah, so that this using MQTT, it gives us the necessary security and connection reliability. And we also do want to preserve battery life, so it's the best option for applications such as this. So it can work with a variety of networks and is supported on both iOS and Android. So yeah, we use JSON for input and output data formatting, storing the data format. And so this semester we upgraded the MQTT package dependency to Cocoa MQTT. And so we made other unnecessary updates and recommendations. So we fixed dependencies, of course, update packages, and we wanted to make sure that the overall application has executable files for next semester. So we initially had, again, focused to make sure that the telescope was moving autonomously or by user code control when we did this, that it wouldn't go into any danger zones where it would hurt the telescope or cause it to crash. But specifically, we wanted to correct the issues regarding the meridian flip so that the telescope, because the telescope can't remember what side of the hemisphere it would be facing when it's shut down. So unfortunately, because of due to the loss of documentation, so that was the main issue we were facing, was that our team had no prior experience using Swift. So to rectify the situation, we actually combed through each piece of code for the Swift control team, and then we at least got the telescope up and running, and finding like the level of efficiency with which the UI worked. And so we were able to at least get a hold of another student from the previous semester, and he walked us through detailing each file, as well as giving us a list of necessary MQTT keys, app configurations, and device information. So our main objective with that for this semester has been improving the documentation to be sure that it's easier and quicker for the next semester to pick up where we left off, and also to have a better understanding of what the telescope does and what needs to be done as far as the programming that we have set up and the goals for this semester. And we also adjusted the layout of the user interface. We added labeling to help indicate motor rates and tracking speed. And so this is also another, this is also a future goal that we want to address, and that is to make it easier for people, for others to use, and that and make it more user friendly. So that includes like adding button features rather than drop down menus. Also, hopefully adding information tabs as a quick reference for users, as well as improving just the layout to neatly accommodate these features. So there are also recommendations of adding like sleep commands and app client to effectively control the telescope. So next semester, hopefully we can continue to work on the meridian flip issues for the telescope as part of the priority.
All right. So we're the IBM Swift Imaging team, and we're responsible for taking the images that are taken by the telescope and then processing them into a final product. Since they're the raw images themselves, they don't have the best resolution, but we take a lot of images, and by combining them and processing them, we can bring out the features that we can see in professional images. So the approach that we go into processing these images is, first we have to organize and divide the tasks between different team members. So we had one team that worked on the flat fielding and another team that worked on the star finding. And like many of the other teams, there was a crash, or we lost a lot of our data from the Google Drive. So we had to find the images from another source. And then we had to apply all the different statistics, physics, math algorithms in order to be able to process our images effectively. So some of the progress we made this semester is we created a flat view, which essentially characterizes the telescope in order to perform color correction. We extracted the color, which takes the images and performs the color correction. And then we have the divide flat view, which also corrects it based on the telescope. There should also be a star finding algorithm that we'll talk about later on. So a few of these are the steps in order to process an image. First, we have to create a dark image, essentially a picture of the telescope while the cover is on. This helps characterize how the sensor itself, if there's any pixels that are naturally on, things of that sort. Then we have a make flat, where we illuminate the entire telescope and then take a picture, which helps reveal dead pixels, if the red, green, or blue is not working. And then we use those to correct for in the actual telescope images. Then we subtract the dark, correct for the dark images. We extract the colors. We correct for the corners, and then we recombine the colors into a final image. So the make dark, as I said, is taken maybe 100 images of the telescope with the lid on, and then at the end, we combine all of those into one representative dark image. And then similarly with the flats, what we do with the flat is we take the flat images, we actually separate them into red, green, and blue, and then we have to shift them to make sure that they're all equal. Because the way that the sensors work is there's more green pixels than there are red and blue. So we have to correct for that in our image processing. And here you can see we have on the left our raw flat file histogram, and you can see how the graph kind of bumps up. But when we separate them into blue, green, red, and luminance, each one of those has a well-defined Gaussian curve. And then after we shift, you can see that the the means are about aligned, and the standard deviations are close enough to each other. before the make flats and the correction is done, you'll see that the standard deviations in the graphs themselves are skewed and misaligned. So once we have those characterizations, we then take our images from our telescope and we subtract the dark. And this is again just to help correct for dead pixels or for any pixels that are naturally on, things of that sort. And then we extract the color from those images, red, green, and blue. And in this step, we apply the same correction factors that we did in our make flats. So these parameters are stored and then applied during extract color. And then finally, we divide flats, or not finally, but like towards the end, we divide flats, which helps correct for the corners because telescopes tend to be darker around the corners of the image. And then we align the color images because naturally galaxies and stars, they move. So sometimes it would be blurred if we don't align. So we align the color images. And then finally, we can combine the red, green, blue, and luminance separately. And then once we have one of each, we can then combine these into final images. And then here are a few examples. Actually, I think there are some new images just waiting for them to load. We did process some new images. There we go. All right. All right, so this is one of them. On the left, you can see what the ROM image. On the right, this is the post-process image. You can see it's a lot more definition. In fact, with this one, we had a slight problem with the luminance, in other words, the brightness. So there is supposed to be a body in the middle that's visible, but that is something that we're working on. But even then, you can still see how the image is much more defined. And here's another case, the raw image on the left, you can see the blur that we were talking about from not aligning the images. And on the right is a post-process image. This one is a little redshifted. Before we fully implemented the color corrections. But even with most of the color corrections, you can see that the bodies are still there. Now here, for example, this is an image that we did just today. On the left, you can see just one raw image. And even the raw image looks, you can see the brightness. But on the right, when you combine all the color images and you color correct them, you can see that it brings out a lot more detail. Similarly here, no, okay. Did I not include the, sorry, give me a moment. They're supposed to be here. Store finding stuff. I think I just imported it wrong. No, it should be there. Sorry, give me a moment. I'll try to figure this out. Transpose. Oh, okay. So I doubled it up. All right, sorry about that. But here are some more of the images. Again, you can see the post-process on the right and the pre-processed on the left. And then, for example, the left is one that we processed ourselves. The one on the right is an industry-level picture. And you can see that a lot of the formations are still there. A lot of the cloud formations were different because these are obviously taken at different times. But even then, you can see that we still have the star formations, the body formations, all of them in the same places. So it's not a bad image for the telescope. And then next we have the star finding.
So yeah, in any given image, there might be more than 6,000 star candidates. And in order to find those, we need to locate the bright spots in the image and label them as potential stars. And then what we do is we create a two-dimensional Gaussian with intensity forming a heat map and using a non-linear least square regression to fit the potential stars. If they can't be fitted, they're most likely like an aberration or an artifact and can be discarded. But if they can be fitted, it's labeled as a star. And it's also important to find the tilted plane of these Gaussians because there might be other sources or other like extinction effects like clouds or light pollution that might otherwise adversely affect the fit. So here we can see kind of like a basic example of what a point source two-dimensional Gaussian might look like. The three-dimensional graph is currently outside of our capabilities using Swift, but the two-dimensional graph is perfectly viable, and we're currently working on that right now. So in this image in particular, there's like 6,200 potential star candidates, and maybe 1% of those might be like artifacts or aberrations that we need to subtract. So we would have to do over 6,000 fits. So we would need a really lean, pretty fast algorithm to make it reasonably timed. And so here we can see like some experimental data that we've done. You can see on the left hand image, the left image is the test Gaussian, and the right image is the fit of the Gaussian. So basically, it's an experiment to see like whether or not we can actually fit this star, and we can within a reasonable degree. So we used two methods. Well, we used some of the least squares, and this middle image here is done over a broad area. But considering the amount of calculations necessary to calculate every single sum of the least squares over that entire area, it is considered like a cost prohibitive and too computationally slow for our needs for the 6,000 computations necessary. So what we did was we used gradient descent, which is a much more efficient and much more expedient algorithm that essentially just finds the slope of the equation and determines where we should guess next. And that is very handy for these kinds of Gaussian fits.
Yeah, that's it. I think next is the observatory team. Oh, I guess they're not here. Never mind.
Yeah, I guess try. Or actually, why don't we have our
I don't know about fearless is the right word, but thank you. All right, so from the observatory team. So our objective for our observatory team was to design a building that accounts for varying programs, ultimately providing a home for our telescopes. So they wanted to find a nice location that really accounted for it being open, with a lot of space for mobility, as well as being quiet as well too. So they came with some different prototypes throughout the semester. Here was one of the precedents. We have the Eden project based on the Grimshaw architects. It offers a lot of different angles that will not only make it very easy, but also I would say access easy for night sky viewing and a really nice location, not really obstructing the view. This is the Rodomes at Miswawa Security Operations based on the in Japan. This is also another location that I think seems to be very accessible as well as very nice for night sky viewing. This is their site right now inside of Montrose County. And here's some of the plans that our observatory team was able to draft with the multi-purpose screening and courtyard. So you kind of see a little bit up there. This is, I would say, a working model right now that we had. And we did have some plans for the future to kind of incorporate 3D modeling or 3D printing to kind of get it into view. So we do want to definitely continue working on that in the next semester. So this is how they would look from a profile kind of view. And this is the aerial review as well. And I believe that's it for observatory.
will be to telescope, right? Yep. Okay, so you're done with the presentation part of it. So let me stop the recording here. We'll say,
application that we have inside of Swift for the control. This is the control station. So through MQTT client, we were able to connect to the server on this MAC address. So this is designed to be remote. So we can actually do this from any location. Right now, we're mirroring from our Mac Mini here at IIT. This function right here, we have standard controls. We can move it for either different coordinates right here. So we're not doing up, it's going up. It's at the max rate right now. We just moved our telescope to due east, so once we move it up a bit, we're gonna actually try to press our due east function, and theoretically it should go back to the starting position, so we're gonna move it a little bit. So right now we're gonna go up, and we're gonna make it turn towards you, the audience. Well, that's actually the wrong way.
It doesn't matter.
Here we go. All right, so we're gonna move it a little bit, and then at the end, we are going to have it go due east. Let's see. So now this is the due east function, so it should go back to where it started. Okay. So it's going a little bit over than where we expected to go due east, but it is trying to navigate its way.
I think it's still moving.
It's still working, yeah.
Yeah. It kind of looks due east.
Yeah, it kind of looks due east from where we started. Yeah, that's pretty much where we started, I think.
Yeah, that's exactly it.
All right.
Now, can you send it to an object?
So we're gonna try to send it to an object. We're gonna try to send it.
Let's make sure it's an object that's visible.
So this, we could try the sun, which is
No.
Okay. We need
we don't want to point it. Yeah. No sun. Yeah.
We need an object that's what's object that's visible right now?
Yeah, I'm looking right now.
Okay.
Okay, something that is visible. We went on the east side.
Yeah.
Leo? Yeah, go to Regulus.
Regulus? Okay. So we're scrolling through a list in our database to see if we can actually navigate to Regulus. And in our database, that's what's on our database. So right now, a database that we're pulling from is a local database, but the schema is set up so that we can pull it from an actual online database. So right now, we have a local database. So we're trying to find an actual body that actually is outside or on the east side, but it's also going to be inside our database. We're going to select Arcturus and we're going to press go. Can we get to the actual database side? Stop works. Okay. It's not select that, I think it's select on the other screen. Wait, here we go. Okay.
So it is moving. The coordinates is moving. It is tracking coordinates for Arcturus right now, but based on our application, it's moving very slowly. I think it's actually, I don't know where Arcturus is.
It's actually just
Right there.
So it is moving slowly?
It is moving slowly. It's moving very slowly, but it is moving based on our outputs inside the application, moving very slowly. I don't think we can really change it into like a different kind of rate. So one thing that we'll implement in the future is for it to go at a max rate to our destination. Right now it moves at a very slower rate, but it is tracking the different coordinates right now for Arcturus. So that the output does, it does have the destination for Arcturus from our due east. Our due east function does work and we can move it manually, but this is something definitely for our improvement in the future.
Okay, let's pause the video.